The order of growth of the resources used by a function or program is a method that computer scientists use to categorize how much resources are used without being entirely precise about the details. So this is a method for establishing a bound on the resources used by a function that scales with the size of a problem. So instead of picking a particular input to a function, we say that the function might take any inputs, and the amount of time or space that's required to compute the result scales with that input size. So we need a free variable in order to describe the size of the problem, and this is often just the input to the function that we're talking about, though sometimes it's the length of the input list or some other characteristic of the input. So n describes the size of the problem we're trying to solve, and we imagine a function r of n, which is a measurement of some resource used, how much time it takes to execute my program, or how much memory is required in order to execute it. Now, oftentimes, this is a complicated function of n, because depending on which branches are followed in the if statements throughout the code, some inputs require slightly more or slightly less time in order to compute the result. The goal of orders of growth is to bound r of n by a simpler function. So an equation that you'll often see is that Rn equals big theta of f of n, where this is the true resources used for an input of size n, and this is some simple function of n, such as n squared or the square root of n. And this big theta establishes a relationship between the equation on the left and the equation on the right. What it means precisely is that there are positive constant numbers k1 and k2 such that f of n bounds r of n both below and above within some constant. And for this statement to be true, this bound must hold for all n larger than some minimum m. You can pick any minimum you want, and as long as this holds for all larger values, then it's the case that the resources used for a problem of size n is big theta of f of n. Now when I write this one long equation, I'm really writing two equations at the same time. I'm writing an equation that says the resources used is bounded below by a function of n, and that it's bounded above by exactly that same function of n, but perhaps with a different constant. So k2 could be twice as big as k1, and that allows this function, k2 times f of n, to be larger than k1 times f of n, and therefore to be an upper bound on the actual resources used. So this can seem a little bit abstract. Let's return to a problem that we saw before and apply the reasoning. So here are two different implementations of counting the factors of n. We looked at a slow way and a fast way. The slow way will describe the time that it's required to compute the result as big theta of n, where n is just the input number that you pass in to count factors. This says that it takes time proportional to the number n itself. Now exactly how much time? Well, there's a bunch of different operations that you do for every factor that you check, and those are all captured in the constant k1 and k2. We also write that the space is big theta of 1, meaning that it's constant. No matter how large an n you pass in, the amount of space that's required to compute the factors is just the fixed amount, because we have a fixed number of names in the implementation of the function. So the bigger the n you pass in, the more time it takes, but the space doesn't really change. Now what about the fast way? Well, the fast way we say is theta square root of n. And that is a different order of growth, because square root of n grows more slowly than n. Now this assumption about constant space actually assumes that integers also occupy a fixed amount of space, no matter how large they are. And that's true for basically every integer that you'll encounter in your regular life. But if integers get really, really big, 2 to the 1,000th power, then they start taking up more space. But let's not worry about that for now. Let's focus on this difference in the ordered growth in the time that it takes to compute factors. And I'm going to show you the difference by actually measuring how much time it takes to compute each one. I've switched into an environment called the Jupyter Notebook, which is just another way to write Python code. I've actually executed all the code already. It takes a little while to run, so I'm just going to walk you through what I have. I have the implementation of divides, factors, and factors fast. And then I have some code to actually compute how much time it takes to execute these functions. So timeit's a built-in module that allows me to repeatedly call a function over and over and over again and record how much time was spent executing that function. All this stuff allows me to draw graphs, and this computes the median and particular percentiles. Okay, so I'll just walk you through this quickly. We're going to take in a function's name, and we're going to take in a bunch of different arguments to pass to it so that we can try different values of n. And then these I'll describe later. But the point is that it constructs a function call as a string, and that's what we pass in to the repeat function, which is part of Python, the timeit module. So it's going to repeatedly call this 25 times. It's going to do that 25 times over, take the median of medians, and end up with a typical amount of time that it takes to execute one of these functions, where we're either going to call factors on arguments from 20 up to 1,000, or we'll also look at factors fast. Okay, so when you call factors, here's the plot that you see. On the horizontal axis, we see the size of n, all the way from 20 to 1,000. And here is the time in microseconds that it took for a typical call. So you can see that it's not a totally simple function because it's so jagged. Prime numbers really only have to add once, whereas numbers with a lot of factors have to add many, many times. So you're kind of doing the same number of divides that scales linearly, but the other stuff that you have to do in your accounting bounces around a lot. So this is a complicated function, but you'll notice it kind of looks like a straight line if you ignore all the jagged stuff. By contrast, factors fast doesn't look like a straight line. So here's the same range of inputs from 20 to 1,000. Here's the time in microseconds that it takes for a typical call. This is even more jagged, but you can also see that it's curved. So at 200, it takes kind of between 60 and 80 microseconds, but at 400, it takes kind of between 80 and 100. So this is not twice as long as that. It curves and slopes. And exactly what shape is that slope? Well, it's not a line. In fact, it's a square root curve. And the way we can see that is by passing into plot times the linear function for factors. And it's going to look for constants, k1 and k2, which determine the slope of these two lines. And these are supposed to represent the lower bound and the upper bound in the order of growth equation. And you can see they nicely sandwich the actual amount of times in red with much simpler slopes, with much simpler functions. If we apply the same reasoning to factors fast, this time we're going to pass in the square root function in order to determine the bounds. The plot times will look for constants k1 and k2 to multiply by square root of x, and you can see that this nicely bounds the lower end of how long it takes to execute this function. And this square root curve with a higher constant k2 nicely bounds the maximum amount that it might take per n. So that's what we mean by order of growth, is what shape of function do you use for the lower and upper bounds so that it sandwiches in all the actual running times, or you could apply it to the amount of space used, etc.